Hey everybody, I'm Lucian Mincu and I'm here with Adrian Dobrita. We're both technical co-founders of MultiversX. We're building one of the most advanced technical technologies that scale trust, truth, and human collaboration. This is a front seat into the journey we are taking to build this tech and share it with the world. We talk about challenges, experiences, setbacks, laughs along the way, and lesson learned. Today, we're having a special episode because we're going to talk about something we both deeply care about, which is the Andromeda protocol release inside the MultiversX ecosystem. So please sit back and enjoy the journey. Hey, Adrian, how's it going?
Hi. Really good to be here in this podcast. It was a bit sudden, but maybe this will make it more interesting.
100%. I think this is what's going to make our episode special. I'll maybe just give a bit of context. So during the last days, actually, I've been discussing and sitting a bit with Adrian and going through the breakthroughs, trying to comprehend, follow up with all the efforts that the protocol team was doing. And I had a moment after, while discussing and actually finding and learning myself all the progress that the protocol team is doing. I sat back afterwards and said, it's rare to remember or to listen to such stories and extremely hard to comprehend from outside what it takes actually to build this kind of technology, what's the process, and once people will listen again in the space, this is, I think, the most pure version of how people could appreciate this kind of technology. And this is also, I think, one of the reasons why we're both here and how we learned a lot in the space, actually. There were other people that were extremely passionate, extremely crazy about their vision and executed that inspired us as well. But maybe going back to and doing a very short intro. Adrian, great to have you here. Very excited actually to chat, and then also very curious maybe to share a bit of context of maybe what's your background, just brief background before Elrond, just a brief context about that.
Yeah, sure. So I've been basically working on tech for at least 10 years, I think, before we started with Elrond. We were, actually, that's how we met in Munich. I was working there, and of course, Romanians in Munich, we had our chances of meeting up with multiple occasions. This is how we actually connected. But I was working at that point, I was working at Intel, working on completely different stuff. Like I was doing mobile, I was working on mobile drivers, sensors, battery charging, all those stuff, accessories. I was working, as I mentioned, for Intel. Previously, I was working also for Samsung. I was doing also some projects for Apple and so on. There were many companies I was working for. Some of them directly, some of them like freelancing through other companies. But yeah, my background was mostly technical. I finished computer science, and since I started all the story with the computer science and my experience afterwards, I was constantly interested in new tech and let's say cutting edge technology.
100%. I can confirm that. I can also just share a bit that I think we met 12 years ago, maybe something like that, Adrian, together or something like that in Munich. And from all my friends, Adrian always stood out. Also extremely humble. Not only that, I was always fascinated how big brains, so to say, extremely bright brains actually can also both be very simple humans, very beautiful humans, actually, in the sense of the way they be, but also fascinating once you have actually had to chat around what they are deeply passionate about and what they were doing. So that actually was maybe one of my first interaction with Adrian, and then of course, maybe to go a bit further on. Once we came to the idea actually to build something like this, I was thinking, who are the brightest people, friends also that I ever met, and that they could ever comprehend at that point of time anything that crazy. And Adrian was indeed not only to comprehend, but actually a brilliant mind to build and co-found actually the entire tech journey of this tech powerhouse that we're building. So again, Adrian, congrats, respect, and keep up the awesome work.
Yeah, thanks. Also, congrats to all the other members of the team. You as well. You were hands-on. At least in the beginning, you were always hands-on also on the tech part. Now a bit less, but
yes,
still, yeah.
yeah. I mean, on the one hand, there's my way, maybe a bit just to state my way of being was actually, how can I help everybody around to succeed, and I will do that with the deepest heart and with full power. And at that point of time, my first challenge was actually to bring the smartest people to work on this or work together on this challenge and journey. But then once this succeeded, the second problem was, who are the second batch of people that could follow up, catch up with the knowledge that those brilliant friends are actually building around, and then they can support this kind of talent. It's always like in a concert, you have this solo players, and then you need an entire orchestra to play around it. I was trying to actually be every instrument around the solo players and try to do my part. But thank you very much. Maybe going further on, and then very curious, Adrian, how do you see, maybe in short, after 7 years of building, how would you describe the protocol, maybe in short? What's the way you would describe MultiversX protocol as it is today, and what it differentiate compared to other ecosystems?
Well, yeah, that's a difficult question. It's been a long time, 7 years. Wow, I'm still surprised. But I think we managed, like in a very small size team, actually. We are not a really large team on the protocol, but in this setup, we managed to be really agile, I think. And currently, we're basically like an engine, like everyone has the things pretty clear, like what they're working on, what's the purpose, what they're doing. We're also well coordinated, I would say, inside the team and on the goals we have. Yeah, I think we managed to do a lot with really small resources, little resources. 100%
agree, and I think this is also a blessing on the one hand, that allows us to cut a lot of the overhead of coordination, and then also be in the hardcore startup mode. So fully agree on that. I've been there, been with the core team, with the protocol team day and night, and I can just relate how great it feels also to achieve, look back and then look of the achievements. Maybe, but on the technical way, if you would look from a bird's eye view on the protocol specs and design and architecture, how would you describe it maybe in the version as it is today? Maybe just from where it starts and then how.
Yeah, so I think we are like the original design we started with. It has changed in multiple places, especially now with Andromeda. But I would say the outline, it basically stayed the same. We are still trying to build a very scalable solution, and compared to other ecosystem, I think we did a pretty good job on achieving it already. on the efficiency as well, we like with every single release we rolled out, this has been one of the goals to build an efficient system. This is also what you can see from the specs we're having for all the machines. Like the entry level for people, for validators on the chain is really low compared to any other ecosystem. From what I know. I think now with the latest upgrades, so with Andromeda and also the upcoming Supernova, I would say that we are there in the top from the tech perspective, and the entire tech stack that we managed to build, and not only on what is visible from the outside, but also around all the tools that we are using to validate and to improve on what we are building. So it's like the iceberg where you can only see the tip of the iceberg, but there's a whole lot more that you cannot see, but it is there, and it helps with everything that we try to roll out.
Fully agree. Maybe also sharing a bit of that is also especially that if I share from my view, not only, so there, I think there's two sides of the problem. One's the speed of execution and the advancement, but then again, the orchestra, like how fast can the solo player, so to say, go and play, and how fast the orchestra can sustain the entire throughput, and then still have a masterpiece at the end without breaking anything. And this is especially, it's a factor of I think discipline, quality of tests and procedures, and testing as well, a lot of testing. And that was one of the challenges, or I would say from what my point of view was, literally try to find the ways to literally make sure that at least the same amount of brain power or efforts were put to make sure that the artist is sustained to achieve that. So in this case, you are the artist, Adrian. I think especially for that, you did an amazing job. Maybe curious, just to move and explain a bit, what are the, like, how do you see maybe the other scaling solution? Maybe just to put a bit in comparison, what stands out? Like, what are the frameworks that, so maybe, and I'll help define a bit how people are looking from outside. So on the one hand, there are maybe ways to scale consensus. There are people that are scaling a bit of the state access with caching, a lot more caching. There are ways to maybe just do storage, a lot more storage. But then how does this, in which box, and actually how do you see this? Just putting a bit of context again for people, why it stands out to the architecture.
Yeah, so I really like the analogy with the orchestra, because it's a really different story when you have a solo singer in front and he doesn't need to coordinate with anyone else. But then if you have a large scale orchestra, every single, like any mistake, any synchronization mistake could ruin the entire piece. So it's a really good analogy, and we're at that level currently. So a lot of what I've seen in the space, especially from sharding point of view, because there are a lot of projects now mentioning, or they are either started working on sharding, or they have been working on sharding. But from what I've seen until now, none of them were really sharding at the level we have built. So we started in 2019, no, not 2020, it was the release. But since the testnet phases, before going to the mainnet, we already had a full state sharding solution. We were having this binary on machines, on separate machines that formed separate shards, and the state was divided on not one machine having the entire state of the entire network, or doing only logical sharding. It's much easier when you're doing logical sharding, like you have the entire state of the machine, of the network, and then you just use part of it, but you still can synchronize it much easier with the entire state of the network. It's a completely different story when you build it like in the real sense, where you really have distributed machines having divided state, like a subset of the state or a subset of the actions they need to execute, or the subset of transactions, and you do not have, or any single machine does not have the overview of the entire network, but it still works correctly. So I think this is the end goal that any state sharded solution should have, and this is also the solution that would practically scale, because otherwise you still have the same limitations that you have without sharding. It's just like playing sharding but not really executing on that. So from this point of view and the decentralization point of view, I think we did a really good job by having this solution ready in 2019, 2020 when we launched, and now of course still working on optimizing stuff, on making it more efficient, faster, and so on. But these are already like the cherry on the cake. The main problem was already solved some time ago.
Fully agree with that. So I was having a podcast yesterday and trying to explain in layman terms what we did, why did we choose that, and what was actually a contrarian, why it was a contrarian bet. And I was explaining a bit like, if it's like you have a computer that you can, of course, it can solve, you can turn it on and you can work with it to solve the problem of today. You would just need to add more RAM, more CPU, how long, to the limit of that, what hardware limitations are, but and definitely you will solve the problem of today. If everything we're looking at and we're trying to solve is to actually get one task done, which is actually get 10 transactions per second, whatever today's needs are, and we can fulfill that, then of course a computer or just a server or just a simple server or something like that in that spectrum would solve the problem. If you would go and say, and try to argue to your investor that you're building a data center and you first need to lay down the cable, the infrastructure, the entire, and then for now you're just starting the data center with the server, that's hard to explain a bit. Hard to say, hey, so you're telling me that there will be so much demand in the future for this kind of stuff that it will be, you won't be able to scale from a server without the entire infrastructure around to a data center, but rather build the data center, build one minimum computation unit, and then be ready to scale up with the network, with the needs of that. Curious if it resonates a bit of what the state of blockchain technologies are when they are just caching the state a bit more, implementing a bit deeper, just the one of the particular engineering implementation compared to literally fundamental building a different contrarian bet which would actually play out in 10 years, 5 to 10 years, whenever the industry will pick up this kind of crazy demand. Curious maybe if it comes close to this kind of analogy as well.
Yeah, I guess definitely it is. So there are different views, and I can relate to both of them in some sense. But mostly I relate to building the foundation right, and then scaling on that. If you build the foundation right, you can also have an early validation that your idea would work. It's much more difficult to try to figure it out on the way, and then building it in we also use the analogy of changing the engine while the car while you're also driving the car, which is pretty difficult. And we've seen that with a few releases where we changed some of the let's say core parts. It's still very difficult to achieve that, but laying the foundation right can give you a perspective of what are the problems that you will also face further down the line, and try to come up with solutions before the time you reach those, or those problems find you. So I think from this perspective, having the outlined system and having the validation that the system works and improve on that is it's like, from my perspective, is the correct way to set that. But I also see the value in starting small and then extending on that, because it gives you like an advantage on starting early, like front running competition, or this kind of starter advantage, first mover advantage.
100%. There's always a trade-off of resources and time, right? So whatever you can decide to focus on, it's a limit. You have, especially as a startup, limited resources where you can allocate towards, and then you take a few bets that you think that will have the maximum outcome in the foreseeable future. But yeah, fully agree that I think and believe that the more time we spend in this market, in this industry, the better and the most reliable and more valuable this becomes. And speaking about that, I think generally feedback was after the last 4 months actually being running around the globe, that people or most relevant players decided to say, okay, we're going back to fundamentals. And that's, I will repeat again and again. And back to fundamentals means that pretty much most of the most valuable technologies that are, especially in the same sector as L1s, they do have one particular narrative, which is increased bandwidth, reduced latency. Now, speaking about that, I would love to double click and maybe go a bit deeper into the engines room and talk about what is Andromeda? What does it bring? What, maybe define a bit the scope of how the protocol worked until now, and then what is Andromeda high level, and then we'll double click on some of the breakthroughs, because I think this is just something that extremely hard to comprehend from outside.
So I'll try to maybe reduce the problem on a few main points. I will try to discuss. So when we started, the consensus model was also adapted to our view back then. And the limitations we saw on like the processing, what is the average latency between nodes all around the globe, what could be achieved with the cryptographic solutions we had available at that point, and also our understanding of the field. And from that perspective, I think we took the best decisions we could take in that setting. And to give a bit of a context, what I'm referring to is the design of the consensus, especially where we had several limitations, like as I mentioned, what is the latency between the average latency between nodes in the world, what was the ideal setup of the network that we wanted to have eventually, and to give some numbers, we knew we want thousands of nodes, more than thousands of nodes. We knew that we want to have a level of scalability where you could create potentially thousands of shards. We knew that we wanted in each shard a high enough level of security, so we decided that the minimum number of nodes per shard would be, and we decided there that it should be between 400 and 800 nodes. We computed back then what, like depending on this average latency that we were measuring, we computed then what would be the round time, or how fast could we achieve consensus with these limitations, like having a block being agreed on by a set of nodes of 800 up to 800 nodes per shard, and have enough time for all the processes during the state machine of the consensus to finalize, because you also have time boundaries on each of the steps. Then what is the context this consensus needs to be achieved in? Like, you're working in a adversarial setup, you have a BFT setup where nodes may be malicious, may be offline, may have faults, and we kind of put all of those together in a group. Like, we have this number of malicious nodes we need to account for, and then what is the level of or what should be the design of this consensus so that we account for those malicious but still achieve a very, very high level of security for the consensus, because we are working with money, and normally when you're working with money or safety, then you need to ensure that the security is very, very high. So we had a lot of limitations. Also, I mentioned about the cryptographic solutions and the specs of the machines we were considering at that point. If you remember, I think the specs we were considering were in the first, what we started with was 4 gigabytes of RAM, if I'm not mistaken, and 2 CPUs. And we were considering if we should drop it to 1 CPU or still mention 2 CPUs in the minimum requirements. So we actually built for that. And even now, if you could still run those specs, of course, we increased a bit the specs. We are now, I think, at 8 gigabytes of RAM and 4 CPUs, which is still...
I think my phone has 32 or 64 gigabytes. So nothing common. Even the fridge right now has more RAM than that, I guess.
Yeah. So even now, I think we are one of the ecosystems where the minimum specs, or the entry level with respect with the specs that you need to have to run a validator are like really cheap hardware. It's really cheap hardware. But still, in these conditions, we wanted to have like very, very high level of security, and this also influenced a lot the design we had for the consensus. Of course, it was not our a problem with no solution. There were already solutions that we took a look over, like we already had the PBFT, and which was used also in several ecosystems, like it was Cosmos. There were others as well. So we had also some examples, and we built on that. We took the parts they did research on, and we also improved on by ourselves, and we achieved the first design.
Maybe pausing here and doubling down or double clicking on the first design. How many steps of achieving consensus maybe? Or besides, so it's great that we lay down a bit the premise or the primitives on which we built the architecture, but also maybe double clicking on some of the specifics of the consensus. For example, which would actually build the case a bit to the next step to what are we doing with the newer upgrades.
Yeah, so it's a bit hard to remember, but if I think well, I think there were around 5 or 6 steps in the initial design for the consensus to be achieved. Yeah, because
yes, I forgot. I always at least erased my memory with the 4 or 5. I kept the 3. 3 were, I think it was the upgrade, right?
Yeah.
One of the upgrade.
Yeah, one of the upgrades were with the 3 steps, but originally there were 5 or 6 steps because we were also doing like we were using all the steps in the classical PBFT. We were also doing the change view like inside the consensus. Now, at one point we removed this step because we already had a way to synchronize having the same view over the network. We had very strict boundaries for the consensus slot, and the decision on what is the final view of the network over something that has passed or not passed consensus, we were doing through other means. So we managed to remove that from the consensus and achieve a bit of a speed up. Of course, there were also some drawbacks from moving from the full number of steps originally designed in the consensus to fewer steps. And one of the drawbacks, I think it was that we needed we had some equivocation risk, and we needed to have a way to mitigate that equivocation, which we were doing through confirmation blocks. So that's the point we added the confirmation blocks, because initially you would have one-shot consensus, but you could not have bounded it really well in the time limits we were working with.
I'm trying to pause you, Adrian, and then play the curious guy, and then try to translate a bit. Ask you to translate what is for our listeners. I hope they will still have the patience to follow us through, but and I'm sure some of them will share it with their brightest minds, friends. But what is maybe the principle of maybe first, what is a practical BFT method, or where does it come from, just to at least translate and go back and give some fresh air for people, and then what is equivocation also, before going and diving deeper into that.
So this is like a solution for a problem. The problem is achieving consensus among many participants in this protocol when you have faulty or malicious actors in this setup. So the context comes from the Byzantine problem, where with the Byzantine general, I won't get into details.
It takes too long.
We will extend this episode too much. But the problem is how to achieve consensus when you have malicious parties. And this is the problem, and the solution was the BFT. You had the BFT solution, but you didn't have the guarantee that this protocol works always. Without adding some special time limits, some time boundaries on messages, on message propagations. So in this case, the PBFT came as a solution. Yeah.
BFT, maybe just saying the full name for people to allow them to search after, is Byzantine fault tolerance and practical Byzantine fault tolerance. I'm just adding two caveats here for people to pause the episode, go look at how they work, what do they imply, if you want to understand and contribute to this kind of technology. Now go. Please, Adi.
So the problem was defined and the solution as well. So the BFT and the PBFT was defined with certain parameters where in this context, or the assumptions of the world, the problem was in, and what is the solution, but applied to those assumptions. If you go outside of those assumptions, like one of the assumptions is that you do not have more than 1/3 malicious nodes inside this world. If you go beyond that, then you need to also adapt the parameters that were provided with the solution. How you can achieve consensus with this setup, you would need to adapt that as well. But if we're using this context, then the solution was providing clear. So there was a clear solution for this context that you can achieve consensus in a time within a time boundary. The problem with that was that the boundary was very elastic, and we wanted to work with very short rounds where it was a partial synchronicity for our defined problems. Like we wanted every consensus to finalize in what we computed that would be relevant to have all these operations being done. And at that point, it was 6 seconds. How we can achieve consensus within 6 seconds. And then, of course, with the equivocation that we introduced, if we stuck to the first design of PBFT, it would be more elastic, but from the time perspective, the time it took to finalize it, but you would have the result. You would not have the chance of having missed consensus. It will always finalize with consensus on something. Here, the problem was with the changes, the leader could introduce some equivocation because we had this strict limit of stopping the consensus at 6 second boundary. You could have, in case of a malicious user, that malicious user could stop the consensus, but then propagate messages which would appear that consensus was actually reached, and propagate those messages at a specific time when another block came into the story, and then end up with two competing blocks with the same height or nonce, and then the network needs to decide which is the canonical path they need to follow. So this is also a bit explaining what is the equivocation in this context. Of course, there were also some other possibilities of equivocation, but this was the main one that would have arise from the design of our consensus.
So maybe translating again in very simple steps. So how previously our consensus method worked, I think it was the 3 steps. You have the leader, so you have a slot of 6 seconds. You have a leader that actually proposes a subset of transaction. Then it broadcasts the system enters in the step 2 of the consensus, which is actually at the final step of the step 1, the leader proposes and sends the subset of transactions that he selected for everybody to achieve consensus on. Then everybody, the entire network, has the time reserved to participate in that, and then send their signature or vote on that particular computation back to the leader. And then while actually the previous state was that the leader should aggregate all the signatures, and then what happened, assuming, for example, that we achieved all the computation, but then you have a hiccup on the internet or whatever, there's a malicious leader, it could actually prevent or hold the piece of information that will confirm that and finalize that particular block production, actually, which would be a valid one. And then even if it would just hold it long enough to just pass around, and then because you need to have a system where you have some sort of a delta on the latency on the network, it could come that it will be propagated to a slightly over time slot into the newer round. Maybe I hope I translated into more simple for our listeners, just to which will actually conflict with the next round, which implies that the system should build on top of the previous block. Now,
exactly.
This is exactly so that just helping a bit and translating a bit. Awesome stuff, by the way. Cool. So this was, I think, the current previous version. What is the newer design, and what is Andromeda bringing in, and what were the rationales while building this?
Yeah, so maybe I would offer Another bit of context on the previous model, so that I can give enough space to the Andromeda with all the improvements we've achieved there. So if we go to the previous model, as you explained it, it had those steps, and at the end, the leader was supposed to finalize the consensus round by aggregating the votes and then propagating those. And if at that point it was either malicious or faulty or offline, then it would probably introduce some equivocation. And then let's say the mitigation for that was the confirmation block. This confirmation block, basically, the effect it had was adding some latency on the finality of a block. Because it could be contested, a block could be contested, it needed the specific mechanism to solve this conflict. You basically needed the slot for a confirmation block in each of the shards. If we consider that we had 6 seconds per block, per consensus round to be achieved, and then another 6 seconds of another consensus confirming the first one to avoid this, then for all the cross-shard operations, you basically had these 2 blocks on the source shard, 2 blocks on the notarization shard, which is the meta chain, and then 2 blocks on the destination shard for the cross operation to be completely finalized. And then this time to have the results of the execution of a transaction, this is actually one of the problems, or the increased latency we had with the previous model. Another problem I would like to, maybe it was not very obvious, we had a different set of like a different setup of the consensus group. Who needs to achieve consensus? So each of the shards, the setup was we had 400 nodes per shard. And then in the meta chain, we already had full size consensus. So already each block had maybe up to 400 votes, but they needed at least 267, which is 2/3 plus 1, in order to achieve consensus. Then on the shards, because we wanted to allocate more of the round time for execution, we added a smaller consensus size, and for that we had 63 out of 400. But then if you have agreement between 63 or 2/3 plus 1 out of the 63, you cannot have a guarantee that the majority of the shard agrees with whatever was proposed, even if you have a past consensus round. So then besides needing to solve equivocation, there was also a need to guarantee that the majority of the shard agrees with the proposed block. And here it is also one of the reasons we needed or a confirmation block, because if you start and compute the probabilities of what is the probability that the majority, which is 2/3 plus 1 of the shards, agree with a block, if you have a confirmation block, when you work with 63 out of 400 taken in consecutive steps, but then out of the 63 you have only 2/3 plus 1, which is 43 that need to sign in order to prove that consensus was reached. So there was also this problem to prove to the meta chain, which finally does the notarization, that there is already sufficient agreement inside the shard over a proposed block. Because otherwise you might end up with the malicious group. So this is also the context we computed the probability. What is the probability that in a population, initially I think we started with 25% world, or a world where 25% or up to 25% of the world are malicious, but then we extended, I think in the paper, in the white paper, we still have 25%. But then we extended it to what is the probability of having a 30 or 33% malicious, which is the classical setup of a BFT. So in this context, you need to also take into consideration that some of those nodes are malicious. And then when you compute this probability, you need enough security, you need to guarantee enough security that a maliciously proposed state transition or transactions in a block do not get notarized. So what is the probability for that? And we try to contain that probability, to have a very, very low probability for it to be negligible. And in the context of this was also one of the reasons we had to add the confirmation block. Like, it was not an option; it was like a demand to have that in order to maintain a high level of security. And if I remember correctly, I think what we computed in this setup was something around, with a confirmation block, we would go to something like 10 to the minus of 21 combined probability that in a world of 25% initially malicious, you do not end up with the possibility of notarizing a badly proposed block. And if you look, also we computed the same in the setup of 33%, 33% malicious. But there's also another level here of the problem, where you need to consider also that you have a dynamic number of shards, because our solution was designed to be adaptive. So we started with a setup of having, 3 execution shards and 1 metachain that does notarization, but this was not the final setup. So in the initial setup, this worked with 1 confirmation block. But then if you extend this setup to 10,000 shards, for example, then you would soon realize that this setup is not sufficiently strong to avoid a maliciously proposed block being notarized. And in this context, I think the computation was something like, if we extend with the same number of confirmation block, you would end up with 1. So the original setup with 4 shards, it was 1 in some billion years, 160 something billion years. And the second setup, where you extend to 10,000, it was 1 in 44 years, which was not something we wanted, because we designed for more than 100 years anyway. So this was why also the confirmation would have been dynamic. The confirmation number of rounds would have been dynamic, and adding another confirmation block would have completely removed any possibility, but then you had even higher latency for cross-shard operations. So now that I put this problem also into from this perspective, I would go to what happened with Andromeda. So we wanted to remove completely the confirmation blocks, and thus removing the latency, and have a really efficient consensus. You have one-shot finality, and then we building on top of that, we can reach also sub-second. Because in some sense, I think moving from Andromeda to Supernova, it's a bit simpler than moving from the pre-Supernova or Spica, which was the latest one, to Andromeda, from the point of view of the complexity of the problem. The other, of course, also for Supernova, we have different things we still need to change, which takes time, but the problem is not that complex anymore. So it was really important to get this first solved, to have one-shot consensus without any security issues with the new design. So then we can go even maybe below 400 milliseconds and so on.
Pausing here and trying to again to just get the fresh air inside the room, and then translate a bit for our listeners a bit, maybe few of the concepts. So if I can summarize it correctly, and please correct me if I'm wrong. So on the first step, we had pretty much this kind of 3 steps, where the third step was particularly needed to aggregate the block, and then broadcast and consider it as a final one, which had few consideration. One, security, of course, but then also we had also some extra some extra steps actually attached to that one, if I remember correctly, was the rating system of the protocol, the reward distribution and computational system that was also attached to that part, but also on the same time, so it added security, but also had the problem that which you were defining earlier, that if the leader, for example, gets offline through the process, the block would be aborted and it needs to entirely be recomputed, even though the entire 2/3 of the round was exactly honest and good work by the entire participants. So that's one of the problem. And then also, while if we go and say, hey, we want to achieve a super high efficient, low latency system, then any kind of step inside this kind of processing system needs to be reanalyzed, which, for example, is on the one hand latency, network latency, removing. So what it translates, if we are considering to optimize anything, we need to look at the very deepest steps that are required in order to achieve that, which is latent network communication, compute, and other raw materials which should be considered in the steps. So actually, this is a bit for summarizing a bit that what are the consideration besides security also that we are considering. Besides security, I'm mentioning and I'm pausing here, security is the most important part actually. But in order to achieve that, you are also working with some raw materials, particularly on that, which is communication, computation, and other stuff. So pausing here a bit and then giving you again the mic to how this actually looks looking forward. And not looking forward, actually, again, clarifying, it is live on mainnet. We are talking and recording this podcast, especially to give an insight of what has been achieved in the latest 2 years, actually, while we were working hardcore on this, and what are the changes. Now, Adrian, please.
So there needed to be a few steps in order for Andromeda to be possible, or the changes in the consensus. We, of course, wanted to have also on the shards 400 out of 400, because then a few of the problems I mentioned would have been completely gone. For example, what is the probability that the entire set of or the entire shard has a majority agreement over what was proposed in the context of malicious as well. So this one, if you had full size consensus, then this one would be solved. But because or the computation for validating that the entire set of nodes has correctly participated in consensus and have given their vote, aggregating those votes and so on, at least this part was also a bit inefficient in how we handled it before. We have since then moved to, for example, we were using inside the aggregation scheme, we were adding protections for rogue keys, which is when someone is simulating that he has a key, a public key for a private key that doesn't even exist, so that he can influence the voting with more power than he actually has. And we were embedding into the aggregation scheme this kind of protection, but that also introduced a latency, or no, a compute time which was higher than what you would have had otherwise. This was one of the reasons we wanted in the initial design, or we decided in the initial design that we need to have 63, because for that set of validators it was less time consuming, and then you could have more of the round for execution. But then we moved to knowledge of secret key, which we already had actually through the staking system, but it took us a bit of time to realize that actually we can use that instead of the embedded protection. So we moved to that, and also we changed to optimistic aggregation, where you only do the validation at the end for the aggregation. And then all these changes and some others has allowed us to really reduce the computation time for checking that the voting was done correctly and there were enough participants in the voting process. Was reduced for something like more than 1 second in case of like I'm counting here all the operations needed to do this on a two CPU machine. But then in this context, we reduced it to below like a matter of 10 milliseconds right now. So it was needed. Some of these optimizations were needed in order to increase the consensus size for the shards. And then, as I mentioned, some of the problems we originally had with the agreement on the block having already been solved through this. Then the equivocation for that, this is also implemented in Andromeda. We wanted a way to avoid equivocation, even though we still keep the same number of rounds, or even try to reduce the communication rounds. So in some sense, you had more communication rounds before because you also needed a synchronization between the participants. Now, for the last step in the consensus, you just need to fire and forget because you can you don't need to wait to see that there's an agreement, because you can already see on your side that there's an agreement on the block. And now I'm getting into a bit of details why it is like this. So the model has changed to something like the leader proposes a set of transactions, then you have everyone voting, including the leader. Everyone votes by sending their signature on this block if they agree with the proposal. And at the end, like everyone is receiving these votes, everyone inside the shard, because only the participants in the shards are interested in these kinds of votes. Everyone inside the shards receives these kinds of votes, and on their own side they can aggregate. They can aggregate if they have sufficient votes. They can aggregate the votes and see that the aggregation is correct by doing, as I mentioned before, optimistic verification. And then they already have the proof that the consensus was reached, but they also can broadcast it, this proof. It's not necessary to broadcast the proof, because if you already have it, probably the others already have created it. But in order to reduce the span of the block, it's also useful to propagate this. And we're propagating it now not only to the shard, but we're also propagating it to metachain. The previous design was that a block proposal was done inside the shard. Then everyone computed, checked that the block is correct, checked that the result is fine. They voted, they agreed, they aggregated, and only after you have the finalized block together with the proof for the block, which is the aggregated signature, they would broadcast it also to the metachain, so that metachain can do the notarization when the time is right and they have sufficient confirmations. Now, this setup meant that you have a latency between propagation of a agreed upon block to metachain, and the time that metachain also needs to do the verification and has the time to include it in or notarize this block. What has changed is that now we no longer need to adapt the block. So the original block that is being proposed goes directly to the shard and also to the metachain. So you save some time on propagating maybe large blocks if the case is that there will be larger blocks with more transactions. You save a lot of time because you propagate this early. And then you just need to propagate the proof that consensus was reached, and that happens faster now, because we are also not waiting for the entire set. Previously, we were adding some time boundaries where we need to cut off the consensus, and if we have enough signatures or votes, then consensus was passed. Otherwise, consensus was considered failed. But we needed some cutoff, but we added that cutoff time around the end of the round, and we were waiting for more than 2/3. Regularly, we were waiting for most or all of the signatures to be present, because we were using this also inside the rating system and the reward system as well. Now we're if we want to focus on speed, then we need to cut off the consensus when we have a sufficient number of votes. So currently we're just cutting it off when we have 2/3 plus 1, and we have changed also the design of the rating system and of the reward system, so that validators that are a bit slower are not affected by these changes, and they can still participate in consensus, earn rewards, and secure the network. I don't know. You were looking like you wanted to add something.
Yes. Again, trying to simplify on the one hand. Again, just to restate in simple words. So in practice, you would have let me do it this way. So in practice, we had until now a consensus round of 6 second 3 steps. And then which were leader, consensus, leader again, which actually broadcasted to visualize for our audience the one that looks in parallel. You have also the meta chain, so assume that you have 3 layers that are shards that are broadcasting, and then overhead, or you have also at the same slice in the same time actually also meta chain producing those blocks. Meta chain were previously 400 validators per slot, where shards were actually 73. The upgrades that we are talking about first increases on all the shards the 400 actually participants, so 400 of 400. Why and how we are achieving this is because we reduced the number of communication overhead, and we also measured, I think Adrian was specifically, I don't think you mentioned until now the latency within the slot. So how did we came up with this magic number? I'll pause and then I'll let you a bit to say how did we came, why 600 milliseconds and so forth. But then what we were saying before is that the newer upgraded version, we figured out a way to drop the latest need of one particular single actor, which is the leader, to confirm or do the job, and actually democratize that particular role to any kind of participant inside the consensus. So in simple words, if we all listen to the same channel, and I'm proposing and giving to 400 people a task, and then we are all communicating back through the same channel where everybody listens within that subset of people that needs to complete the task, then the primitives that we have built allowed each of single one of us to aggregate. So in order to consider the completeness of the function or the task, it is everybody will give a vote, which is equivalent of a signature. And then those signatures could be on each of our own books aggregated without the need of someone superior to do the job. And while doing that, I also figured out a way to translate in simple words. In cryptographic numbers, there is no such thing as 200% correctness or it's either you're incorrect or you're correct, right? And then when it comes to security, or validity of a message, when you're looking at the validity of the block. The block, it needs first to just wait, so to say, to have the 2/3 plus 1 confirmation, which makes it 100% correct and valid and secure. There is no such thing that it will make the block 200% secure by waiting another 4 seconds or 10 seconds or whatever on earth the laziest machine will wait. So in practice, if all the machines are good and fast enough, what Adrian was mentioning or what you're saying is that it actually, if in 1/10 of a round, all the machines have completed the job, we can already aggregate each of us and reach the conclusion and send it, since all the slots are working at the same time inside the system, instead of us waiting until we finish and then entering with the message into the next block on the meta chain. You actually shortcut and give you ahead this kind of message ahead that will help. So I just tried a bit to translate it into a visual version, how at least our listeners also might help them understand. But now, going back, maybe how did we came up with the number with the number of that's the next one. That's sorry, that's the supernova. Maybe you still
No,
sticking to that.
it's good. Maybe I will go to how we came up with the 6 seconds.
Yes.
Because we did some measurements and also had some estimations on the average latency between machines on different continents. And we had to measure the average number of hops inside the network for a message to reach the majority of a shard in this context. So also considering the number of synchronization steps or communication steps we had inside the consensus round, all this together with the processing time slot that we had until now considered and so on, we came up with the 6 seconds, which would have covered. I would never say 100% of the cases, but 99.9% of the cases. Now, coming back to today's or to Andromeda, we have decreased the number of synchronization steps a lot. So in this sense, you can see that there are actually 2 steps for synchronization, and there's another one for propagation, but that can happen asynchronously. And for this, you already have lower number of latencies you need to add for the propagation between the network. We also have increased, in some sense, the number of peers, so decreasing the number of hops through the network. And then you also have lower latency. Currently, today, than we had 7 years ago when we started. Working on these problems. So we can also reduce from this point of view our assumptions about the latency. We did measurements over the network, but we added actually on the mainnet, on some nodes we had observers and some validators that we were running as well on the mainnet. We added some patches to actually measure what is the current state of the mainnet. And according to those measurements, we ended up with the conclusion that we actually can do the consensus, even the old consensus. The old consensus without moving to Andromeda, we could potentially do it in 400 milliseconds. But there's a but here, not doing also the processing during the consensus. So we need to separate the consensus part over the ordering of the transactions and what is the set of transactions we need to execute and the actual execution. And in this case, you can get below 400 milliseconds even with the old consensus model. Now, we have moved to the new consensus model to Andromeda, and this one already has some improvements over the number of steps you need to do, over the number of signatures you need to wait for. So in this sense, we could go even lower, but as a first step, to validate everything, because you always find out other stuff that limit you. Also, like it happened, but maybe that we'll get to that in a bit with the Andromeda patch 2. We found out we introduced some latency which we needed to solve for supernova, and you always have some things that you weren't foreseeing before, and you need to come and solve them. So we kept, I would say, enough tolerance in a 600 millisecond round to cover like unforeseen issues that we need to solve. But definitely we can also improve on the runtime in the future. Now, I wanted to also give a bit of a contrast with the previous consensus model with Andromeda. Like currently, the chances of producing with Andromeda, the chances of producing an invalid block that gets notarized by meta chain.
This is a very good metric. I love it.
Yeah, this basically moved from 10 to the power of minus 20, I think, to basically zero, even if we increase we increase the number of shards to 10,000 and we don't add any confirmation block. So this type of problem ensures that even in a future where we have hundreds of thousands of shards or even millions of shards, you do not have a higher than once in a million years chance of producing a block where a metachain notarizes it and the block was actually invalid. So in this sense, I think we have improved a lot on the security. We have improved a lot on the latency, and now we can build on top, reducing the latency or the slot for a block to be produced.
Fully agree. I think if there's one point that actually when thinking in systems stands out is whatever you have noise or waste or any kind of inefficiency inside a system, when you scale it up, that scales up with the system. So
and normally it scales up faster than the system.
Especially when it comes to network topologies or communication and stuff like that, that the way the algorithms work, I think it just I think this is one also maybe just to say and make a bit of a funnier break here. It's I think today or yesterday was Bitcoin Pizza Day. Luckily, we the guy who ate the pizza, I think he will be remembered for the rest of the time. But looking back at Bitcoin, I think if you would want to scale up Bitcoin, not only the algorithms and the block production structure, but one of the biggest and the fastest bottlenecks will be the network topology, which allows you to propagate the speed of the message propagation in order to achieve any kind of consensus on top of that message. And when it comes to, for example, 10,000 peers or 10,000 node participants or 100,000, if we're talking especially on a network that will scale to maybe 100,000 or 1 million participant machines, in order to propagate without a center point where you just spam all other machines and actually you have a distributed network that maintains also the low latency and high efficiency and extreme low noise. This is, I think, looking at every single piece of information that needs to be broadcasted and the distance between is, I think, a mandatory step in order to not end up with any kind of any kind of similar state of network as Bitcoin. But yeah, that's a very small break, I would say, that was also why and what actually compounds to any kind of future advancements. But very curious now, going back to speaking of efficiencies, what were exactly, for example, the time boundaries on the computational steps that were compared to you were mentioning to Andromeda patch 2?
So while working on Andromeda, as I mentioned that we have the iceberg where you can only see the tip, we have worked a lot on also tooling that can help us validate Andromeda, and not only validate that the consensus works, but also validate that the performance improves or it doesn't drop. The performance doesn't drop. And for this, we added several tools. Actually, we have we already had tools before, but specifically when moving forward with higher rate of block production and with such a big change in the consensus, we needed to have other tools as well. So we built chaos framework where we can introduce chaos inside the network and see that it behaves correctly and it takes the correct decision on the level of the network, even if we introduce faults on specific nodes, on subsets of nodes, the network still goes forward and survives this this chaos. Also, what we wanted to see, what is the performance with the changes that we added. We always had this in mind that okay, the first step we are building it, but then how does this relate to the future advancements that we need to do with Supernova? Because yes, of course, we could have went out with Andromeda like in December, but it was not yet as efficient as we needed it in light of Supernova that was to come afterwards. So we had introduced in the first patches, in the first versions of Andromeda, we had introduced some performance degradations on the CPU, and I'm going to give some reasons for this.
So I think it's yes, from the outside you would say consider the degradation in the sense it would be a lot just heavier because of some of the functions, extra functions needed in order to cut to shortcut the processing time and maybe the but this is not, it is degradation in the sense that it could, now looking backwards to where we got right now, yes, it is degradation, it is less efficient, but at that point of time it was at any point not obvious that it is a better path. But they're just clarifying a bit here, but sure.
Yeah. So we knew that we were going to add some more stress on the compute size, since, for example, I'm just taking one of the features that entered into Andromeda. We introduced the so-called equivalent consensus proofs, which is the way we avoid equivocation now with Andromeda. And you mentioned it correctly that any node inside the shard can provide a proof that consensus was reached. There's no longer a need to rely on the leader of the consensus round to provide this proof. Anyone can provide it. The drawback here is that if anyone can provide it, consider that you can build such a proof from 2/3 plus 1 of the possible 400 votes. Now, if you consider what combinations you could get out of those, it's I don't want to compute it right now, but it's about beyond trillions of different combinations, which are all correct, but you do not like, you could flood the network with those types of messages. So we needed to add some protection in the network that this flooding does not happen, and we added that as well. You also need to in some cases, you can end up with two such proofs that you would need to in some way process. But then how do you overcome that? How do you stop the flooding in the network in this way where you have different originators? Like we already had anti-flooding mechanisms where from messages from the same originator, if they are the same message, they are dropped, because you can also have different paths of propagating, and you can have the same message which started in a single point get to you through different paths. So in this sense, we already had a way of avoiding those before, but now the problem got even expanded a lot, because you can have multiple points that can start the propagation at the same time. In one sense, with this possibility of having multiple points that start propagating a similar message, in this case a consensus proof, it actually helps speed up the time of propagation. So in this sense, we can reduce a lot also the time from the beginning of the round until the consensus is seen, that is reached by the entire set of the nodes, including metachain, which needs as well to receive the proof. In this sense, we have also improved a bit the time to see that consensus has been reached. With the changes that we've done on the anti-flooding mechanisms, we have solved the anti-flooding problem, but then we also had an added latency on the proposal part. So when you propose a block, the leader in the first patch of Andromeda, in the first version of Andromeda, we had the previous, like the proof for the previous block also added on the header. But what that added was extra validation time for each of these types of messages, which then if you multiply by the number of steps this message needs to pass to reach the set of nodes that need to have access to these messages, then you would have an increased latency. And this is what we had for the meta chain to receive this kind of proof. We had an added latency of, I think, between 60 milliseconds and 100 milliseconds. So this latency we had to solve. Yeah, go ahead.
Yeah, pausing here and translating again a bit. Just step by step. So the in the new proposed version is that actually while we are removing the step where, if I go back to the story, while we're removing the step where the leader actually will sign and make only one piece of information valid, that will actually be eligible to be broadcasted. So and again, double clicking on how the broadcast mechanism works, I produce because for example, we are 400 in a group, because you know that actually I am eligible for you to communicate with you and talk to you, and you gave me a piece of information, and we started the next sub round inside the consensus where you were waiting only from me to broadcast you or originate a message from me that you will consider and put it in the slot, which you will build. Whoever that next leader will build on top of that information. Because we removed that, we needed to add some security primitives, where security is again algorithm mathematical computation, where in simple, it's a receipt. Almost like a receipt, which includes a key, a security key. But then if everybody can produce the key and everybody could add from those 400 in a different order and only one different key, because the distance or the propagation between the messages were different in between those 2/3 plus 1 from the 400, it's enough, which is 100% that on every machine, assuming that they are only in two different locations, they will have different random message time to receive those messages actually, and then consider them. It's obvious that the keys will be different, and then verifying those keys also takes a lot of time. So this is, and in order to broadcast what you were saying, in order for this message to be eligible to be broadcasted again, the function on each of the nodes is, okay, I know that you are 400 are eligible to send me a version of themselves. And in order for me to rebroadcast and enforce or redistribute their message, I need to also verify it before, because otherwise I would just allow the network to be spent. Is that correct? Like this is, yes. And then
the problem is even larger, because if you have a malicious node, he can broadcast different versions. So it's not limited to 400 messages. It can expand to trillions, as I mentioned.
Yeah, you can just actually, assuming that so what you're saying, assuming that I'm already inside the 400 set and I'm just modifying my binary, I could have just produced in that specific time-bound system enough messages to keep everybody busy, not being able to consider the correct version of the node. So then I think this is how you got to we got to the second point, where we needed to get rid of the need of that particular so just, I hope I clarified and just simplified in simple, again, a bit in simple words for everybody around.
Yeah. So of course, when logically designing the new consensus flow, or you have the theoretical model, but then you need to put it into practice. And into practice, you need to take consideration of timing. You need to take considerations of malicious actors as well, and how the problem can be like this problem is one that is exponential. It can become exponential as well. So we needed to ensure that we have all the measures that this problem cannot happen, not on such a scale that it can damage the network. So what we managed to do is actually, compared to what we had previously, even though we changed this design with all the things that we've put into place to prevent the problems, it's actually on the bandwidth side looks the same. So it's I think we did a really good job on that. I think I wanted to add another like side of the story here. Together with these changes, since we know that there's also the sovereign chains being developed and improved on, we wanted to add also some improvements for them. And especially what part I'm referring to is the bridges implementation. So currently, if you want to verify that a consensus was reached, and I'm talking here on the previous version, on Spica, for example. If you wanted to prove to a different chain that consensus was reached on MultiversX, you had to have several pieces of data sent over so that they can do the validation. And what type of data was needed? Like, who was part of the consensus group? What order they had in the consensus group, what was the original order, and we had like subsamples of 63 out of 400, where the order, since you have 63 out of 400, the order could be very, very different between each subset. What we wanted to do is, and this what did this imply for the problem that I mentioned of communicating cross chain, or proving cross chain that consensus was reached? It meant that every single block that you wanted to pass through such a communication channel between chains, you needed to give also the data. How was the consensus group selected? They needed to have the logic of selection to verify that the selection was correct, on the basis of what was what was the random seed for that, what was the ordering, or completely embed the logic in on the other side, and then feed this data so that they can verify every single block. Now with the changes with the Andromeda, since we changed to have 400 out of 400. Also on the execution shards, we no longer need to have a different order. So we no longer need to have a different ordering on how we aggregate the votes. And in this sense, you no longer need to pass data every block to the cross shard in order for them to verify that the ordering is correct, and to have the knowledge of verifying the aggregated signature to see what was the subset this time. It's always the same set of nodes. It's always the same 400. It's always in the same ordering. And now you just need to mention who or what is the position of the ones who signed, and give them the signature. So it has decreased a lot the number of or the size of the data you need to pass over for a bridge, for example, to validate. And this we added as well in Andromeda.
I mean, crazy to as I started the podcast, I don't ever imagine that anyone from our listeners could comprehend or foresee actually at least 10% or 20% on the thought process and the efforts got here. Also, yes, indeed, mentioning the sovereign chain, actually, that everything that we're building at the protocol level will be inherited on the sovereign chains. That is almost the new kid in town, I would say. It just if the family and the family speaks a new language or develops some good habits, I mean, the new kid will most probably just most probably will get a bunch of those new features, as I would say. I'm curious. Maybe going back to the overall Andromeda release. What else should we cover? I think so. Just to restate, pausing maybe here for our audience, everything that we have discussed related to Andromeda is live on mainnet. So it is actually deployed. We are pending. We are recording this podcast actually pending activation. But compared to any kind of previous discussions where we were discussing only what we're going to do, this time we are here saying that this is just a tiny bit of the journey that the protocol team and MultiversX has been actually putting a lot of effort and building this kind of technology stack that actually will pave the way, the path actually to scale up a system in such a way that will reduce latency, increase bandwidth. Now, I'm pausing here and then curious if you want to add anything specific first to Andromeda, and then just do a short hint on what is needed and how this builds up to the 6 seconds, and how could actually look like if we would look forward towards the protocol, and why do you think also that it is, or we think that it is actually to the limit of what the blockchain computational possibilities are actually achieving with the upcoming releases and the path we are going towards.
Yeah, so with Andromeda, we actually have instant finality. Every block, if the block has a proof, it's final. It's already final. It cannot be reverted, and this simplifies a lot the logic of also integrators that need to interact with the chain. Also, applications that are built on top, and here applications I'm referring especially to bridges. Because you know instantly that if a block is produced, it is already final. Then it simplifies because you have this type of synchronization between the shards as well, like the meta chain and the other shards. You need to what it does, this simplification, what it does, it reduces a lot the complexity of handling blocks. For example, on the meta chain, it simplifies a lot how many blocks it needs to track, when it needs to decide to notarize a block. And as you know, for the cross-shard operations, meta chain until now, it was like instrumental because it was giving finality to whatever happened inside the shards. Now with this change, even though we still maintain in Andromeda, we still maintain the same path where meta chain still notarizes and keeps track of the cross-shard operations, which are split into steps. Like you have the step of execution, then you have the step of notarization, and then you have the step of execution on the other shard the transactions are interacting with. And in this sense, with Andromeda, you basically can skip the meta chain notarization because it's already final. So you can have that information passed over to the cross shard and then reduce another round in the cross shard communication. We didn't add that into Andromeda because we would have delayed a bit, but this is also a potential case to come after Supernova, where we reduce again another step inside the cross shard execution.
So what you're saying is, because going back to my example, because we're actually cutting the last round, and we are actually being able to so we have slots that are actually equal and being produced. And then on the one hand, you were starting originating with the message in the shard 0, because we are eliminating and we can broadcast the block confirmation and successfully block production and eligibility to the meta chain before it starts its block production. It will be included, and because this one will as well finalize and finish its block production, which includes the previous source message in its block production, it could be again also considered and eligible for right away the next block in the destination shard. Is that correct?
It is correct, but also the notarization on the meta chain would not be mandatory. Like you could have it as a just bookkeeping. You can have it as a bookkeeping, but the cross shard does not need necessarily to consider that, because it can have direct access and direct verification that it was correct on the source shard. And then it can be included. If it follows the protocol rules, it can directly be included. Of course, this change, as I mentioned, would need some effort as well, and probably it will come, but after supernova.
I still think each time when I'm having this kind of discussion and visualize, I think you've been working on processor architecture and microcontroller architecture actually, and looking how threads actually work, and knowing that pretty much the way I visualize beacon chain or meta chain was always the thread safe execution environment, which actually doesn't allows which or coordinates the threads which data should touch and is safe to touch on. Now with this, the way I always envision in order to make the CPU faster is not only just add more computational power to it, but actually reduce or increase the speed of coordination between the threads or the tasks that are being able. And this is particularly not actually adding any kind of overhead or almost zero hardware costs in terms of that compared to what we were having, but actually reducing the time to load, boot, so to say, or access any kind of task that is coordinated. Is it?
Yeah. I think the analogy is good. Yeah.
I think on the one hand, we are literally on the very, very hardcore low tech that is, we're literally measuring any kind of bytes and pieces. And then also towards that, I was, I was telling you that or wanted to tell you actually when we discussed about the latency that, or I think I briefly touched on, assuming that in a future version with this kind of setups that we are building and variables that we are building on each of the execution steps, assuming that the network latency will decrease over time and we will find a better version to communicate and broadcast messages over the globe, as for example technologies as 000. I was discussing a bit with the guys from Jump the last days, and they were telling me, so look, so we are building this because we are coming from a world where every kind of milliseconds counts, and we are making dollars or money on top of that because we are actually building on the trading engine. So we have the discipline since 20 years to build this kind of super low latency machines. So we in order, so on the one hand, it is the scope of the validator or the block production to be super efficient, and this is actually what we've been working on. But there are some other problems that are less in our control, so to say, which is the topology of the network or the message propagation systems. But assuming that we will find or tap into this kind of future systems that have direct bandwidth or latency cut between the hops over the internet, they were saying, so look, there might be a way to actually talk to Japan and Europe in 20 milliseconds. So achieve consensus and connect those kind of super hardcore technical software or pieces to this kind of hyperlane backbone around the globe, where we could produce and synchronize and achieve consensus in 20, 50 milliseconds for a round. So we were discussing around that, and then maybe wrapping up the podcast soon. And curious, I think, what were the conclusion? Assuming that we will have a system where close to 20 milliseconds, 50 milliseconds will be just the overhead of latency for the consensus. What are the current steps that you think could be achievable in the foreseeable or very near future with the protocol to synchronize this kind of network?
Yeah, so for the topology, you mentioned that topology is not in our control. Topology of the network, it is somewhat in our control. We already have some rules for the network sharding, so we already have some experience with influencing the topology of the network in this sense. Of course, for the supernova, since we want to have 600 millisecond rounds, at least in the first stages, we are already working on having faster propagation of messages, especially transactions, so that we can ensure that the round can finish in 600 milliseconds. So this would be one of the first steps we are trying to validate. But then on top of that, considering these types of latencies that could be achieved between continents, of course, this changes also the type of solution you would want to add. But the good thing is that this can be an addition and not a complete overwriting of rules. It can be as an addition to the current setup of the network, where we can benefit from this type of really fast broadcasting of data, so that we can reduce the latency across consensuses between different rounds. It's definitely, we can go to fast block times. I would say we just need to take it gradually, because otherwise the problem becomes too large, and you would spend too long time to come up with the final solution.
Fully agree. What I was mentioning when it comes to topology, I was mentioning the physics underneath physics. That's just to make sure. Which underneath physics, you could still use the same copper or fiber channel, but there could be 100+ millisecond difference per pocket broadcasted, just even though you're achieving the same source and destination, because you're not prioritized, or because you are actually broadcasting a message over a public infrastructure where as in blockchains, some transactions are prioritized, some transactions or some pockets are prioritized given the price they are paying. The same way it is also with the physics, underneath physics over the world topology. So I think there are some interesting experiments, but maybe to conclude on that, we were discussing, and I think I was asking Adrian, what's the raw computation need at this point, knowing what we know today in terms of milliseconds, if we would consider zero latency overall. So can we achieve 200, 150 milliseconds, 100 milliseconds only compute? I'm crazy and just pushing the limits, and I see that you're already smiling and avoiding me. But just trying to close up and maybe wrap up in a crazy path.
Yeah. So for if we consider zero latency, we would probably be okay also with around. Or we could go below 200 milliseconds.
Interesting.
The thing is that we're maybe I'm giving some alpha. We're
that's my job here. I learned from my best.
Yeah, we're also working on parallel execution. Of course, that is not the priority right now, but we have a prototype for that. And in order for that to achieve its potential, we would need a bit more time on the propagation of the message, so before the proposal. In that sense, I would say there we could go to the lowest we could go to achieve the potential of parallel processing. It would be 300 milliseconds, I would say, considering zero.
Considering so yes, indeed, there are 2 points maybe to define. So on the one hand, is not only quality, it's also not only quantity, it's also quality of computation, and then the structure that we need to pass through and achieve consensus on is also relative to so rephrasing this, if we knew that, for example, and could redesign everything from scratch after 7 years with the maximum computational primitives that are available today, definitely there might be some different structure or some smaller different data structure that we would have implied. But nevertheless, I think the progress that we are making and the optimization are actually bringing us into a crazy good outlook that actually looking at bare bone computation stuff that we are doing inside the system, there's extreme low waste of time in all kind of layers. So when it comes from topology, from processing, from consensus, from everything, where we were from the state that we started with 3 seconds, the consensus was just free up from the work, where we're looking at every kind of piece of the thread inside the CPU, memory allocation, and all kind of stuff to literally squeeze all the juice out of that box without increasing the hardware requirements and achieving a 20x just compared to the previous state of the network in the upcoming to networks. I think it's just mind blowing. It's crazy to look at.
Yeah, definitely.
I think we covered a good step for today, Adrian. If you want to have any closing notes that you would want to share for us.
Well, not necessarily. Very excited for the activation of Andromeda, and we're already fully hands-on on Supernova. So expect some updates on how that's going as well.
Hardcore, Adrian. Deep respect. Love it. I hope everybody could see at least a bit better, 1% better. How Benjamin will say and understand a bit better what we've been working on, focusing on, and we will continue to do on. And also, I hope our love and passion could also broadcast and penetrate a bit your ears and get to your heart and talk and look deeper into what we're doing. Thank you very much. This is the Full Shot Podcast, and I'm here with Adrian. Was a pleasure talking to you. Thank you, Adrian.
Thank you.